Welcome, Calculus AB. This is 5.3 inverse functions and 5.4 exponential functions. Let's begin. So this is a lot of review here, so if you know a lot of this, you can skip it. Inverse functions, what are those? Basically, they're functions that undo each other. It's almost like opposites in a way, or it's like going backwards. So for example, if f of x equals x plus 1, the inverse of that is g of x is x minus 1. And the way you get this is like set this to y equals x plus 1. Basically, you want to rearrange this to solve for x. So how would I rearrange this? Okay, I would just subtract y on, or not subtract y, subtract 1 on both sides, and you'd get x equals y minus 1. And then flip the variables here, so you get y equals x minus 1. And that's what you get for g. So it's just about flipping it. I can do the same way with g. So let's take the g function, switch it to y equals x minus 1. I want to solve for x instead, so I add 1 to both sides, and I get y plus 1 equals x. And if you flip the variables, you get your y equals x plus 1, which is the same thing as f. So it's just like setting different variable to be the what you're solving for. Over here, these are inverses as well, because if I set this y equals to 4x, and I divide it by 4 on both sides, you get x equals y over 4. So again, flip the variables, y equals x over 4. These are inverses, so you're just solving for the other variable. Alright, we have inverse notation. So if f of x equals 4x minus 1, instead of saying f and g, we can say inverse f of x. That means that little -1 sign there. And if you've seen that with inverse trig functions before, you might have seen this before. So that -1 sign means the inverse of the f of x function. Okay. So, for example, I can just do this. Let's rearrange this one. Y equals 4x minus 1. So if I wanted to solve for x instead, when I add 1 to both sides, let's get your y plus 1 equals 4x. Divide by 4. And you're going to get your x equals y plus 1 over 4. Flip the variables. Y equals x plus 1 over 4, which is exactly what you get for the inverse. And it'll work both ways. So we have this fancy definition of inverse functions here. Inverse functions, you can take the composition of two functions and they'll equal x. So the composition of a function and its inverse will equal x. So let's actually prove that. Let's take an example. I have this example. F of x equals 2x cubed minus 1 and g of x equals the cube root of x plus 1 over 2. So we got to prove these functions are inverses. So it's got to work both ways. I've got to take f of g of x and then I also got to do g of f of x. So let's do the f of g of x first. If you do that, that's going to be f, so that's f of this cube root of x plus 1 over 2. So what you're doing is you're plugging x cube root of x plus 1 over 2 in for the variable x, and that'll equal 2 times the cube root of x plus 1 over 2 cubed minus 1. The cube root and the cubed cancel out, so you get 2 times x plus 1 over 2 minus 1. Those 2's are going to cancel out there. So you're going to get x plus 1 minus 1, which is going to equal x. So that checks out. Let's try it the other way. So g of f of x, which is going to be equivalent to g of 2x cubed minus 1. So I'm plugging that in for the x. So what I'll get here, I'm going to split this up. I get the g function, which is going to equal the cube root of not x plus 1 of 2x cubed minus 1 plus 1 over 2. Alright, which let's combine terms in that radical, or that fraction. So 2x cubed minus 1 plus 1, those cancel out, so I get 2x cubed over 2. And those 2's are going to cancel out, so I get the cube root of x cubed, those cancel. And the cube root of x cubed, those cancel each other out, so you're just left with x. Hey, that works out. Cool. Alright, how do you determine if a function has an inverse? So we just determined that the inverses can equal x, the composition of them. So, oh, my board just died. Come back. There we go. How to determine if it has an inverse? Two things. Function has an inverse if it is 1 to 1. That means for every x value, there is only one y value. And for every y value, there's only one x value. I'll show that with a graph, what that means. It also means it'll pass the vertical line test and also a horizontal line test. It's not organized well. But so if you do a horizontal or vertical line, it will never cross more than once. Okay, it's also strictly monotonic. What does that mean? And if you remember, that means derivative, or f prime of x, is always positive or negative. It doesn't flip. It's always positive for everything on the domain. All right? So let's use those. I want to prove that an inverse exists, because sometimes we don't just want to find the inverse. Like, I don't want to find the inverse of this. This is actually really hard. I don't know if you can. But I just want to prove that an inverse exists. So here's a graph of that function. It looks like a cubic function here. And one thing you know with it is it's going to be one-to-one because it passes the vertical line and horizontal line. If you draw vertical lines, you're never going to cross more than once because it's always going to left. Domain is infinity both directions, and it's infinity and the range in both directions. And again, horizontal line test, you'll never cross more than once on that function. Cool. So now let's actually prove that it's monotonic. So I'm going to take the derivative of that function, f prime of x, is going to be 3x squared plus 1. So what's cool about this is always going to be positive, because no matter what you put in for x, it's always going to end up being a positive number or 0. So if, like, the worst case, this is 0, you're going to have plus 1. So it's always positive. So that's monotonic. So we're good. That has an inverse. Yay. All right. Other thing. This is in section 5.4. Exponentials and functions. Just want to do this quick. Just review. This is what natural exponential function. It means that we have this little e here. And e is approximately equal, let's say approximately equal to 2.713-ish, I think. And so this is the natural exponential function, y equals e to the x. And we also have the natural log, ln of x, which is the same thing as log based e of x. So those are the functions we're going to use here. And some properties of natural log, the natural log of e to the x is going to equal x, and e to the ln of x will also equal x. They kind of like cancel each other out. So there you go. Now I want to solve an equation like this. The way you're going to have to solve this is sometimes you have to log or natural log both sides. So I'm going to log both sides of the equation. Now, on this will be natural log of 7. That's just some number. And when you natural log e to the exponent, that just becomes x plus 1. So if I want to solve for x, subtract 1 on both sides, and I get my x equals natural log of 7 minus 1. You plug that into a calculator, you get some value. And there's your answer. I'll leave it like this, though. On this side, sometimes you can exponentiate both sides. That's a word. It's in the book. Trust me. So that means you take e to the power on both sides, and e to a natural log cancels out the natural log, so you get 2x minus 3 equals e to the 5th. I want to solve for x right here. I'm going to add 3 to both sides. And so you're going to get 2x equals e to the 5th plus 3, and divide by 2 on both sides, so your x is going to equal e to the 5th plus 3 over 2. And we'll leave that as an answer. Looks gross, but that's okay. Some other properties you might have to use for exponential, just want to remind you, e to the a times e to the b is a plus b, same base. You can add the exponents. And if you're dividing exponents of the same base, you subtract them. E to the a over e to the b is a minus b. All right. Rules for differentiation integration. I think I've said this in class before. Just I haven't said it officially. The derivative of e to the x is e to the x. It's exactly what it is. And the integration of e to the x is going to be e to the x plus c. So it stays the same. I'm going to take this function right here. I'm going to take the derivative and integral of it. So the derivative, d of x, of e to the 2x minus 1. You're going to have to use the chain rule here. So it's going to be e to the 2x minus 1. You don't subtract or anything from the exponent. E to the 2x minus 1 times the derivative of 2x minus 1 is times 2. So I can write that as 2 e to the 2x minus 1. On the other side, I want to integrate e to the 2x minus 1 dx. I'm going to use my u substitution in this case. And u is going to be 2x minus 1 du would be 2 dx. So I don't have a 2. I got to create a 2 in here. That means I have to put a 1/2 on the outside. So it'll be 1/2 times e to the u du. That's u. And if you integrate that, it'll be 1/2 times e to the u plus c But I got to substitute in. I get 1/2 e to the 2x minus 1 plus c. And there's your answers. And that is it. See ya.